Good morning, everyone, and thank you for joining today's webinar, the Introduction to Liquid Extraction and Solvent Extraction Columns. My name is Mauricio Villegas, and I am a Business Development Manager here at Koch Modular. We have a lot of material to cover today, so I will make our Koch Modular introduction really quick so we can get on with the webinar. Just want to give everybody just a little bit of background on Koch Modular. We are a joint venture with Koch-Litch. Many of you may have worked with Koch-Litch in the past. We have over 40 years experience delivering complete modular process systems to the chemical processing industry. Our capabilities and expertise revolve around process engineering, pilot plant testing, and delivering modular process systems. From a process engineering perspective, we pretty much specialize in complex distillation, liquid-to-liquid extraction, gas absorption, and thermal design. And we also can test those out at our pilot plant located here in Houston, Texas, which Don and Brendan will be speaking a little bit about today because they use that pilot plant when they scale up their processes. And then ultimately, we deliver all our projects modularly. We don't stick build anything. Everything is delivered by truckable module, and they're about 90% complete that way. Everything is fabricated and assembled off-site, delivered on-site, and really all you have to do is plug and play, do the interconnects, and you can be setting up and commissioning within a couple weeks. Now today, just to kind of a little bit of background of what we will be talking about will be liquid-to-liquid extraction and solvent extraction. What we've noticed in the past is many of our clients are either just vaguely familiar with liquid-to-liquid extraction or don't know how really to apply that to that technology to their applications. So we thought that would be a great topic for today. This technology can be applied to various chemical processes, such as specialty chemicals, polymers, pharmaceuticals, food and flavor. Most recently, we've seen it applied to different clean energy processes, metals recovery, heavy metals recovery, bio and renewable fuels. So it's getting a lot of visibility lately. Again, that's probably one of the other reasons why we thought it'd be a great topic for today. Speaking today will be Don Glatz. Don is our Manager of Extraction Technology. Don brings over 30 years of experience with liquid-to-liquid extraction technology, from designing and scaling up processes, and he's written a lot of papers and articles on this subject. Don holds a Bachelor of Science in Chemical Engineering from Rensselaer Polytech Institute and holds an MBA from Fairleigh Dickinson University. Assisting Don is Brendan Cross. Brendan is our principal extraction engineer and has over 15 years experience in liquid-to-liquid extraction and has been working closely with Don doing design, evaluating process development, pilot testing, and also commissioning and startup. Brendan holds a Bachelor of Science in Chemical Engineering from Columbia University. One of the things I wanted to point out is we have a lot of material to cover today. So what we'll do is we'll take your questions in the chat, and we'll collect all those questions and answer them after the webinar. We'll send an email to all the attendees with the questions and the answers, and you can have those available to you. And then we'll also provide a link to a recording of this video so you can reference or share with your colleagues. Wanted to also, just before we get started, just do a quick poll question. Let me share that poll question. Let's see, poll. So here's a poll question, just so we can kind of get an understanding of where everyone's understanding is of liquid-to-liquid extraction technology. Have you been involved in current or past projects? Are you familiar with liquid-to-liquid extraction but never really involved in a project? Vaguely familiar, or you may not be familiar at all and interested in learning more. So we'll give everybody just a moment here to see where everyone kind of falls with liquid-to-liquid extraction. We're seeing about 65% of the audience has answered so far. So in just a few more moments, and we'll see. Looks like so far a pretty good percentage of individuals have been involved. We have about 56%. Involved, 24 familiar, but never involved in a project. Some are vaguely familiar, and about 17% not familiar. So a good mix gives our presenters a good feel for where everyone stands today. So with that, I will hand over everything to Don. Thank you, Don.
Okay, good morning or good afternoon, everyone, whether you're here or in Europe. Uh, so we're starting off here with a slide that basically shows where you would typically apply liquid extraction. You see seven bulleted items there. From our standpoint, we primarily do, I would say 90 to 95% of our work in the first three bullet points. The first one being when you have high boiling organics in an aqueous stream, and the second one being somewhat similar when you have non-volatile components in an aqueous stream. It's in those cases, it's very expensive to boil water away from those higher boiling or non-volatile chemicals. So if you can find a solvent that will selectively extract those chemicals or those metals or whatever from the aqueous stream, that would oftentimes be a much more economical process. Then the third one is when water is the solvent in an extraction process. Typically, if you have an organic stream with something in there that you want to remove, maybe salts, maybe residual catalyst, whatever, and you use water then to selectively extract those materials from your organic stream. So a lot of people have in their plant what they call a water wash. Sometimes it's a batch process, but again, what you're typically doing then is a liquid extraction using water as the solvent. And then you can see there's a few other cases where you might use extraction for various reasons. This slide now shows I picked a few specific industries where and some specific applications for liquid extraction. Certainly the CPI industry heavily uses this technology, and given some few examples there, we've done a lot of carboxylic acid extraction from dilute aqueous solutions, and acetic acid being one of the primary ones. Washing of acids and bases or polar compounds from organic, like I mentioned before. And sometimes it's just simply recovering a valuable chemical from an aqueous stream. A lot of solvent extraction is used in metals and mining, and I mentioned a couple there, copper, rare earths, but there's a whole slew of others, cobalt, zinc, and uranium. Polymer processing uses a liquid extraction quite often. If anybody knows anything about caprolactam processing, there's three extraction columns in every caprolactam plant for purification of caprolactam. And again, some things like separation of catalysts or extraction of water soluble components. Biochemical processing. In the last 15 years or so, there's been a huge increase in the number of biochemical processes we've looked at. A lot of these might be, say, fermentation broths or algae broths. Again, they're aqueous solutions, and if you're creating higher boiling chemicals in those aqueous solutions, then extraction is a good technology. Effluent treatment, certainly if you have wastewater with high boilers in it, again, extraction could be a good application for those. And then I also mentioned there are inorganic chemical processes like phosphoric acid. So this slide shows what liquid extraction is in its basic form. What you have is a feed that has something in it that you want to remove. We call that a solute in an extraction process. So in this case, component C would be the solute. You want to bring that feed in contact with an immiscible solvent. So if the feed is an aqueous solution, that solvent can be many different organic solvents like toluene, benzene, ethyl acetate, MTBE, on and on, things that are immiscible, in aqueous solutions. You want to mix those two immiscible liquids together. And while you're mixing them, you want to effect a mass transfer of that solute from one liquid phase into the other liquid phase. Then you want to separate the two phases. When you do the separation, you get what we call an extract phase. That's the solvent that's now picked up the solute. And then a raffinate phase, and that is the original feed that's given up the solute. Now, assuming you mix long enough to reach equilibrium or steady state here, then when you separate it, this would be one theoretical stage of extraction. And when you look at this stage, you can calculate the fraction unextracted. That's simply how much is not extracted. In this case, we're saying 20%. And then the distribution coefficient. This is something you like to calculate for almost all liquid extraction processes. And it's defined as the concentration of the solute in the extract over the concentration of the solute in the raffinate, again, at equilibrium or steady state. In this case, we're showing it to be almost 8. So a key for extraction is to find a solvent with as high a distribution coefficient as possible for the solute that you want to remove, and of course low as possible for anything else in that feed that you don't want to remove. And then there's the extraction factor. That's the distribution coefficient M times the solvent to feed ratio. And you can see in this case, we're calling it to be about 4. So again, for an extraction process, a higher extraction factor will typically mean you get higher extraction or better recovery of your solute. So 80% extraction, like I showed in the previous slide, is obviously not going to be good enough for most extraction processes. So if you're using a batch process, which we call cross-flow extraction, after the first mix and decant, then you would take the raffinate, you'd add fresh solvent to it, you'd mix it up again and separate it again, and do this as many times as necessary to get from the feed concentration to the raffinate concentration you're looking for. So this would be when you're using a batch process, which we would then call cross-flow extraction. But usually a better method is to use countercurrent extraction. Here you see the same 4 stages, but the solvent now comes into the 4th stage, and then the extract from that 4th stage becomes the solvent to the 3rd stage, and then so on in a true countercurrent fashion. Now, when you run through the same solvent to feed ratio and the same number of stages by countercurrent versus crossflow using the same solvent to feed ratio, you can get to pretty close to the same raffinate concentration. Maybe not exactly the same, but pretty close to the same raffinate concentration. But what you've obviously done here by running countercurrent is you're using only 25% as much solvent in this case as you would have used in a batch process. And now that solvent needs to go downstream and typically be recovered often by, say, a distillation process. And then the bulk of your energy cost is not in the extraction process, but it's going to be in that downstream distillation process. So that's certainly the idea of an extraction column, is to bring your feed in one end of the column. In this case, we're showing the feed to be the heavy phase coming in the top. So say it's an aqueous stream coming in the top. The solvent is the light phase. It's coming in at the bottom of the column. So maybe it's something like, again, toluene that's coming in. It's lighter than water, so it would come in the bottom of the column. And then as these two phases flow countercurrently inside this column, you want to do something to create theoretical stages. So in a column like this, you have 2 phases. You have what we call the continuous phase and the dispersed phase. In this example, we're showing the aqueous heavy phase coming in and filling the column. Therefore, it is the continuous phase. And the solvent coming in the bottom is being broken up into droplets. So that is the dispersed phase in the column. And then you have a primary interface at the opposite end of the column from where you bring in your dispersed phase. So in this case, it's at the top. Going out the top, you have your extract phase, and going out the bottom, you have your raffinate phase. I'm going to talk a little bit later about some specific types of designs for extraction columns and how you create theoretical stages in these columns. So one of the nice things about liquid-liquid extraction is it's really relatively easy to generate your liquid-liquid equilibrium data, which I was just talking about. And this is how we like to do it. We like to use like a round bottom reaction type flask. We like to have it jacketed so that we can control the temperature in that flask. So basically what you do is you put your feed in here, you put your solvent in here, you bring it up to temperature, and then you mix it. We find that for most extraction applications, 2 minutes of high-speed mixing is sufficient to reach equilibrium. You then turn the agitator off, let the phases separate, take a sample of each phase, have it analyzed for your solute, and now you have your distribution coefficient at a specific concentration. You take the raffinate now and put it back in as the feed, add fresh solvent, mix it up again, separate it again, and analyze it again. So we like to do that at least 4 to 6 times to get from the feed concentration to the raffinate concentration that you're looking for. okay? And that's because the distribution coefficient can sometimes change with concentration. And so we like to see how it might change. So when you're doing this kind of work, you can certainly do it to screen solvents. Again, you're generating your distribution coefficient at different concentrations, but you're also going to be performing qualitative observations of how the two phases interact with each other, specifically when you turn the agitator off and how they phase separate. Does it take a couple of seconds, or does it take many minutes for the phase separation? That's very important. When they separate, does something happen at the interface? If you see solids building up at the interface, we call that a rag layer. Or do you see what we would call like an emulsion band, which is the two phases not wanting to separate instantaneously, and they form a two-phase band at the interface? That's important to note. And then finally, you look for entrainment. Is there a tendency for one phase to entrain in the other? Because that qualitative observation plus the distribution coefficient, we need both of those in order to decide what type of extraction column we think is going to be the best column, to move forward with in a given extraction process. So the curve here is, you see an equilibrium curve here on the right, Y being the concentration in the extract phase or the feed or the solvent, and X being the concentration in the feed or raffinate phase. This blue line is your equilibrium curve. So when you did these mix and decants, you were generating this equilibrium curve. So the first point would be the upper point, and then every time you mix and decant, it's going to be a lower and lower point on that equilibrium curve. Now, if the distribution coefficient M is constant, you'll get a straight line like this. But if it's not constant, you'll get a curve. And then once you have your equilibrium curve, and now you operate your extraction column, you can generate your operating line. So the upper portion of the operating line up on the upper right is where the feed comes in, okay, XBF, and where the raffinate goes, the extract goes out. So that would be the upper part of this extraction column where the feed comes in and the extract goes out. The lower part of that operating line would be the other end of the extraction column where the solvent comes in and the raffinate goes out, okay? So once you have these two lines drawn, then using the stepping procedure you use like for McCabe-Thiele, you can calculate the number of theoretical stages that are going to be required for your process. Now that operating line will change depending on your solvent to feed ratio. So as you increase your solvent to feed ratio, it'll move away from the equilibrium curve, meaning you would need less stages. This is some data we actually generated in our pilot plant or our laboratory for a specific application. It was, was a fermentation broth, and we were extracting some components from it. So this red dotted line is the equilibrium curve. We generated 5 or 6 points, to generate this equilibrium curve. And you can see it is a nice curve in this particular case, but not a straight line. The distribution coefficient gets less as you get into low concentration range. So once you have this, and now let's say you want to calculate for 98% solute extraction in a column at a solvent to feed ratio of 1 on a mass basis, how many stages are going to be required in your column? Well, you know your feed concentration, that's a given. If 98% is going to extract, you can, by material balance, calculate your extract concentration. And then you know your solvent coming in, the concentration there. And if 2% of the solute's left in the feed, then you know your raffinate concentration. And you can see with that, you can step off that you're going to need 6 theoretical stages at a 1-to-1 solvent to feed ratio to recover 98% of your solute. You can also make your stage calculations using a Kremser equation, which is shown here. The nice thing about an equation like this is you plug it into a spreadsheet, and very quickly you look at different solvent to feed ratios, and you can look at different number of theoretical stages that are going to be required for your process. Now, the Kremser equation basically works if your distribution coefficient M is constant or is pretty, doesn't change too much. Then this curve, this equation becomes very, very useful for evaluating different types of solvent to feed ratio versus a number of stages. And You can also use the Kremser curves, which are shown here. Here you have the fraction unextracted on the y-axis and the number of theoretical stages on the x-axis. And then these are curves of extraction factor. If you remember before, I said the extraction factor is the solvent to feed ratio times the distribution coefficient, shown down here. Extraction factor, solvent to feed ratio times the distribution coefficient. So just to give you a quick, simple example, if you were extracting phenol from wastewater using toluene as the solvent, which we've done a number of times, we know the distribution coefficient is pretty constant at about 2, and that so that if we used a solvent to feed ratio of 1 part toluene to 1 part of feed with a distribution coefficient of 2, we'd have an extraction factor of 2, and that's about this curve right here. So if you want 99% extraction, you'd go to 1% unextracted, go over to the curve for extraction factor of 2, and it would tell you you need about 5.5 theoretical stages for your extraction process to work. Now, we have a rule of thumb where we target a minimum extraction factor of 1.3 for most liquid-liquid extraction processes. It's a rule of thumb, but it works pretty well. And I think if you look at these curves, you can see why we use this. Because if your extraction factor gets greater than 1.3, you can get down into very, very high levels of extraction or low levels of solute remaining in your raffinate. However, if your extraction factor gets lower than 1.3, you can see these curves are starting to actually asymptote out, and you really can't get to high levels of extraction for many processes with a, with an extraction factor less than 1.3. So this is what a typical liquid-liquid extraction process would look like. The ones we've been discussing anyhow, we have an aqueous organic system with a low boiling solvent. So this is for acetic acid extraction. So if you bring in an aqueous stream at the top of an extraction column with acetic acid, you bring in a solvent like ethyl acetate or MTBE in the bottom of the column, and then you use that solvent to extract out the acetic acid from that aqueous feed. When that extract comes out the top of the column, then you're going to need to bring that over to this third column shown here, which is your solvent recovery column. And here you're going to distill off your light boiling solvent and recycle it back to the extraction column. Coming out the bottom here then would be your aqueous, in this case, your carboxylic acid, your acetic acid, and if you need to purify it further, you might have to go to one more distillation column there. Coming out the other end of the extraction column is your raffinate stream. That's void of acetic acid, but it does have a soluble amount of the solvent in there. If it's ethyl acetate, for instance, it might have 6 to 7% ethyl acetate. So you can see we would typically go to a stripper there. Sometimes that's just a steam stripper. Strip out that ethyl acetate, and then both of these, by the way, overheads going to a single separation drum and recycling the solvent back to the extraction column. So if you look at this process again, as I mentioned before, the bulk of the operating cost is going to be in this distillation step here. Probably 90 to 95% of your operating cost will be in that distillation step. So usually the most economical extraction process is to put as many stages as possible into your extraction column and then minimize your solvent usage, and then you're going to minimize your operating costs by minimizing the cost of this solvent recovery column. I'm going to mention one other type of extraction column just briefly here. There's something, in case you've heard of this, called a fractional extraction. That's where you bring the feed into a middle of an extraction column and you have two solvents, one coming in one end of the solvent of the column and one coming in the other end of the column. Now, we show it here as two extraction columns, and this was an example that we tested in our pilot plant, and we needed so many theoretical stages that it was impossible to do it in a single column. So we had to split the process up into two columns. So in this case, the mixed polymer feed is coming into the middle of this first column. The methanol comes in the top. Now that will selectively, in this case, extract the polar compounds from that aqueous or that polymer feed. And then at the other end here, hexane is brought in. That will flow countercurrently and will preferentially extract the nonpolar portion of it was a mixed polymer feed. So if you balance this right with the right methanol to hexane rate and the right number of stages above and below the feed point, which we did, we were able to recover 99% of one polymer coming out one end of the column, which was called PB here. And then we were able to recover, 99% of the other column called polymer PA shown here with the hexane phase. So that's something called fractional liquid-liquid extraction. I'm going to switch gears a little now and talk about different types of extraction equipment. There are basically three types. There's mixer settlers, which can be batch or continuous. There's column type contactors, which, there's static or agitated, and we're going to talk primarily about packed, rotating, and reciprocating columns in this talk. And then there's centrifugal extractors, which are high-speed devices which force the phases to flow countercurrently. And there's pluses and minuses for each type of these extraction equipment. So we're going to, again, focus primarily on the column type contactors, and certainly a packed column using random packing or structured packing is often used for liquid-liquid extraction. I do not believe there's any difference in efficiency between random packing and structured packing for liquid-liquid extraction processes, and I haven't seen data to really prove there is. And that's because in extraction, we're really not trying to form films on our surfaces. We're trying to form droplets. And then we want those droplets to stay as droplets and flow countercurrently. So the main difference between random packing and structured packing is in the capacity. You can see structured packing has about twice the capacity of random packing, which makes sense. It has a much higher void open area. So when you're designing a packed column, it's limited as to which phase can be dispersed. And the reason I say that is because the material of construction inside this extraction column is very critical, especially for a packed column. In an aqueous organic system, you preferentially want the continuous phase to wet the internals. So if you have an aqueous organic system, water will preferentially wet metal internals. So if water will be the continuous phase, you're going to want metal internals, metal packing inside this column. However, if the organic is going to be the continuous phase and the water will be dispersed, now the organic will preferentially wet plastic internals. So in that particular case, you're going to want plastic internals for your process. Now, so again, material construction is really, really dependent on the wetting properties of the two phases inside the column. And sometimes a packed column can be affected by changes in wetting characteristics, which I've seen happen a couple of times, where you start up a column and it runs fine for a while, and then it starts to lose efficiency. What we learned in these two cases is as something started to plate out on these internals, causing now the dispersed phase droplets, instead of bouncing off and breaking up into smaller droplets, to actually coalesce on the internals, again, which you lose mass transfer area, and those columns started to lose their performance over a period of time. So in those cases, they had to every so often basically shut down and re-clean their column. Poor mix efficiency due to back mixing and wetting. And we just talked about wetting. Back mixing is something that happens in a column, and basically you're most concerned about back mixing of the continuous phase. You really want the two phases to plug flow countercurrently as much as possible. However, as the diameter of an extraction column goes up, the tendency for back mixing gets greater and greater. It's one of the primary things you've got to factor into the scale up of an extraction column. And we've learned how to do that for certain types of extraction columns. So packed columns are not good for fouling services, and they have somewhat limited turn down flexibility. Also, they tend to be best for low interfacial tension systems, not high interfacial tension systems. Okay, we're going to talk about two agitated columns. These are columns that are made by Koch Modular. The first one is a Scheible column, and what that is a series of turbine impellers, and they're sandwiched between inner and outer baffles. If you look inside this circle, you can see what one agitated stage looks like. Again, a turbine impeller in between inner baffles, and then outer baffles or stators, which define each stage in the column. So as this impeller is spinning, it's drawing the liquid in, sending it out to the wall, and you're going to get a circular pattern inside here. And then, so of course, some of the light phase goes up, some of the heavy phase goes down. The reason this column is so efficient is because, number one, you got agitation breaking up droplets, but also you got all this baffling, which helps to minimize back mixing. So this is the highest efficiency of any column available commercially based on data that's published in the literature. Another aspect of the Scheible column is that it has very excellent turn down capability, down to about 25% of design without affecting the efficiency of the process. We don't strongly recommend it for highly fouling systems or systems that tend to emulsify, and that's because we have a different design, a car column, which I'll show you in a minute, which is better for those particular applications. And then you can see here that really these are not high-speed devices that are operating. So the 15 to 75 is a pretty good operating range for most of the Scheible columns that we have produced commercially. Here are some pictures of internals for a Scheible column. The one on the left is about a 6.5 foot diameter Scheible column. So what you're seeing here are the inner baffles and the turbine impellers. In this particular case, the outer baffles would be welded to the inside wall of the vessel. And then on the right side, this is a complete cartridge, which has the outer baffles, inner baffles, and impellers all together. So what you see here are the outer baffles, and you can see we have a Teflon edge here so that when you slip this into the column, that's what seals each stage at the wall of the column. This is a somewhat smaller one. This is a 30-inch diameter Scheible column. And again, you can see pretty good what this internal assembly looks like. If you look on the left, my arrow is now showing you the impeller blade. You see the outer baffles here and the inner baffles in between here. So when this cartridge is slipped into the column, you're going to get a good seal on this. And then we have the car column. Beside the Scheible, there's a number of different rotating agitated columns available commercially, but the car column is unique in that it doesn't have rotating internals, but it has a plate stack that reciprocates up and down. So the key for a car column is what we call uniform shear mixing. With an impeller, you have non-uniform shear across the cross section of the column, but with a car column, you have uniform shear mixing. What this means is you create a more uniform dispersed phase particle size distribution. You don't create fines, and therefore, this is the type of mixing that works best for systems that have slow phase separation or that tend to emulsify very easily. And in the last, like I said, 10, 15 years, we've done a lot of fermentation broths and algae broths, and these tend to emulsify when mixed with a solvent very, very easily. So we almost always end up with a car column for those types of applications. And we've even seen cases where in the laboratory you emulsify so easily that you can't really handle the system, but we can still do that in a car column because there's something about this countercurrent flow and this reciprocating mixing action that allows us to operate with those types of systems. We can also handle solids we've run up to 40% solid through a car column, and that's because I'll show you in a minute what a plate stack looks like. It's all got a lot of open area and nothing, there's no stationary thing, plates or anything inside this column. The whole plate stack moves, so it doesn't really allow any place for the solids to build up. This is a good picture of some plate stacks for car columns. In the middle here, you see this column. It was about 36 inches in diameter, and it has a whole bunch of different plates on it. You look to the left here, it has a perf plate, which my arrow is showing right here, and you can see again high open area, large holes 55-60% open area. They're typically spaced 50 millimeters or 2 inches apart, although we will vary that depending on the mixing intensity we want throughout that column. Then we have these white edged baffle plates. Those are donut-shaped plates with an outer Teflon edge that's higher diameter than any other plate inside that column, so that when you slip this in the column and you reciprocate it, the only wall contact would ever be that little Teflon edge to the wall and not a metal to whatever metal or glass line or whatever you're making your column out. And then we have these spider plates. You can see it over here. And this plate stack, we have one on each end of the column and one in the middle, so that when you tie this whole thing together with these tie rods, that's what makes this a very rigid structure inside that column. And then over here on the right, you see a very tall car column plate stack that's being lifted by a crane. The column shell is now in place, so this will lift up this plate stack and install it into the column. And then once it's in the column, the drive assembly will be put on top and the column will be ready to go. This is another car column plate stack. This one we just installed probably about a month ago. And this was as you can see, a large diameter, but not as tall. And if you look closely, you can see that this has variable plate spacing. You can see open plate spacing in the middle. This was actually a kind of a fractional extraction process where the feed was coming in the middle of this column. And so therefore, a lot of the mass transfer was going on right in this region. So we had to open up the plate spacing because we didn't need as much mixing there. But then we had to close this plate spacing as you moved to each end of the column. In other words, to get better efficiency throughout the whole column. I mentioned data published in the literature, why the Scheible column has the highest efficiency. This is efficiency versus capacity. And you can see why up here it shows Scheible column with the highest efficiency. And then if you go in this diagonal direction, you see the car column. That means it has somewhat higher volumetric efficiency. In other words, it'll be skinnier but taller than a Scheible column, but maybe less volume in the agitated zone. Okay, so before I turn this over to Brendan for this last part on pilot testing, I just want to conclude by saying, if you come to Koch Modular and you wanted to know something about what a column will cost and what design would look like and cost before pilot testing, what we need is the mixing and settling behavior of your feed and solvent. We need your equilibrium data. We need your feed concentration, required raffinate concentration, and your design capacity. With all of this information, we would select the optimal column that we think would work. We'd come up with a preliminary design for that column, a budget cost for that column, and then we would propose pilot testing to truly guarantee that performance. So with that, I'm going to turn it over to Brendan.
Thanks, Don. And like Don said, my focus of today's presentation is going to be particularly on pilot testing and why that's so critical when you're developing a liquid-liquid extraction process. So the reason you really want to pilot test before just designing an extraction column and installing and starting it up is because there's a lot of interesting, complex chemical phenomena that can take place at the liquid-liquid interface. A few of these things are highlighted on this slide. What I like to focus on is whether a system has a tendency to emulsify, what the effect of impurities or solids can have on the extraction process, and kind of like Don was discussing earlier with the packed column, what the coalescing and wetting characteristics are like when you actually have the liquids flowing through an extraction column. So because you can't really predict these things in advance and what impact they'll have, it really makes sense to pilot test an extraction process and then scale up based upon a successful pilot test using the data that you learned from running the pilot test. So one thing Don kind of briefly discussed during his part of today's presentation was you'll have a dispersed phase and a continuous phase and how to make that selection of which is which. This slide shows 4 different possibilities for an extraction process depending upon which phase is selected as dispersed and continuous and the relative gravities of the 2 phases against one another. So for example, if you look at the bottom left-hand side of the slide, You can see here that the solvent's dispersed, the green droplets at the top flowing down from the column, picking up some solute from the feed and leaving as extract with the controlled interface at the bottom of the column. The feed's a continuous phase. It flows into the bottom of the column and then leaves the top as raffinate. But how do you determine which is which? Well, at Koch Modular, we have 4 rules of thumb that we like to look at when we're evaluating a process to make a judgment call on which phase should be dispersed and which phase should be continuous. The first one we look at is just the volumetric flow rate of both phases going into the column. This is the most intuitive, in my opinion, and what you want to do for a sieve tray or a packed column, like Don discussed earlier, is you want to disperse the higher flowing phase. And that's because you're counting on the fixed internals of either of those 2 types of columns to break up the dispersed phase into droplets. So it's easier for those fixed internals to do that if you disperse the higher flowing phase, because that phase will have more velocity and momentum associated with it. For an agitated column, you want to do the opposite. You want to disperse the lower flowing phase. This will lead to better extraction efficiency using that type of technology like a Scheible column or a car column. And that's because you'll get more residence time of that dispersed phase flowing in the column, and you can use those rotating or reciprocating internals to break it up into droplets. Something else we look at is viscosity. And really the key takeaway here is that whatever phase is more viscous, that's the phase you want to have as dispersed. You can imagine if you had a very viscous material and it was selected as a continuous phase, it would impart a lot of drag and resistance to the less viscous droplets either rising or falling through the system. You can imagine if you had something like a polymeric solution with a really high viscosity, if you had that as a continuous phase, it would be very difficult to operate an extraction column. Something else we look at is surface wetting, and Don also touched on this when he was talking about the packed column. The key takeaway here is that the continuous phase, you want that material to preferentially wet the internals. So example, if you had an aqueous organic system and the internals were metal, say for a Scheible column with 316 stainless steel internals, you'd want that aqueous phase to be continuous if possible, because it would preferentially wet those internals. If you took the opposite approach and you had a column with metal internals and you had the aqueous phases dispersed, those droplets could coalesce easily on those internals and you'd lose a lot of interfacial area, as we're showing on the right-hand side of this slide. So you really want to maximize your interfacial area to maximize the amount of mass transfer that can take place. So if you can, you'd like to have the continuous phase preferentially wet the internals. Something else we look at is something called the Marangoni effect. This is the least intuitive of each of these rules of thumb that we look at when we're evaluating an extraction process. But the key takeaway here is that for the best efficiency, if you can, you want to disperse the solvent. And that's what we have found to have the much greater efficiency as opposed to having a mass transfer direction go in the opposite fashion. And one benefit of pilot testing is that although we'll make this judgment call prior to running a test or prior to coming up with a preliminary extraction column design, a benefit of pilot testing is that you can run an extraction column both ways and switch the dispersed phase and continuous phases halfway through the pilot test if you need to really determine which is ideal for the highest amount of extraction for a given application. A couple of things that can happen right at that controlled interface in an extraction column are rag layers and emulsion bands. Rag layers are essentially just where solids build up at the interface. An emulsion band, or sometimes it's called a dispersion band, is essentially where you have droplets forming and building up at that controlled interface due to slow phase separation. So your dispersed phase is flowing up or flowing down to the interface, and it's just taking a longer amount of time for those droplets to coalesce and come together and form a uniform liquid phase. And there's some pictures on the right. You can see in the upper right-hand side of the slide, those are two clear rag layers, where solid black materials building up at the interface. For the emulsion band on the right-hand side, you'll see in the first picture, it's actually the bottom phase that's building up at the interface and taking time to come together and coalesce. And that's a picture of our liquid-liquid equilibrium test apparatus that Don discussed earlier. On further to the right, that orange material, that's actually kind of a thick emulsion band that was at the bottom of one of our car columns when we were running a pilot test. So if left unchecked, both of these types of phenomena can be problematic, whether you're running a pilot test or running a commercial column, but there's a few ways you can combat them from becoming an issue. One is just by simply reversing the phases. This is really effective for emulsion bands because now your dispersed phase within the column is now the other phase, so it may take less time for those droplets to coalesce and come together at the interface. Also for emulsion bands, which can be really effective, is just by slowing down the capacity, so the feed and solvent rates going into the column, or by reducing the agitation speed. If you reduce the agitation speed, you're going to form larger droplets, and those larger droplets should take less time to come together at the interface. For rag layers, what you can do is you can actually circulate the liquid that has solids in it at the interface out of the column and through an external filter. And what we like to do, or what we always do at Koch Modular when we're designing a commercial scale extraction column, is that we'll always put nozzles around where the controlled interface will be. And therefore, even if we don't see a rag layer form during pilot testing, our customers always have the ability to pump liquid out from the interface on the commercial scale and through a filter to remove those solids before they become an issue when running the extraction column. Entrainment is something else that can occur within an extraction column. This is something often we see when running a pilot test. It's essentially where you have droplets going out the wrong end of the column. So you can see in the first picture here, the feed is dispersed. It's going out the bottom as raffinate, but you have some entrained droplets leaving with the extract at the top of the column. And there's a few ways to combat entrainment in an extraction column as well. The first is just by putting an expanded end at the end of the column where entrainment's an issue. By doing that, you reduce the continuous phase velocity in that section of the column, and that could allow those droplets to rise or fall so they can go out their correct location in the column. Something else you can do, as shown in the third picture on this slide, is put a coalescing element at the top of the column or the bottom of the column, wherever entrainment's an issue. And this allows those entrained droplets to coalesce and come together so they go out the right end of the column. This is something we often do in our pilot plant when we see entrainment occurring in, say, a glass Scheible or a glass car column. Something else you can do, and this makes more sense on the commercial scale, is you can take that coalescing element, remove it from the column, put it in an external coalescing vessel. So you're essentially still doing the same thing as having the coalescing element in the column, but now that it's outside the extraction column, if for whatever reason you need to perform maintenance on that vessel, such as cleaning the coalescing element itself, that can be done without taking the extraction column offline. Flooding is another type of phenomena that often occurs in extraction columns, and it's essentially where you're just pushing the extraction column too hard. And that can be done by one of two ways. One is essentially by just having too much feed and solvent going into the column. If you have too much continuous phase flow going into the column, the velocity is going to increase, and it's going to prevent those dispersed droplets from leaving the column. And when that happens, the dispersed phase will build up inside the column, and a secondary interface will form. The other way this can happen when you're using agitated extraction columns, and this is a little bit more intuitive in my opinion, it's just where you have too much agitation. By doing that, you'll form smaller and smaller droplets, and as they get smaller, it becomes more difficult for them to leave the extraction column. The dispersed phase will get held up, and a secondary interface will form, and the column will flood. Now, when we're running a pilot test, we always like to push our extraction columns, particularly from an agitation standpoint, to find a flood point. And there's a few reasons for that. One, is just good to know where and under what conditions the extraction column will flood. Also, it's good to know how difficult it is to get out of a flooding situation in an extraction column, whether that's just cutting off feed and solvent, or reducing agitation speed, or cutting off feed and solvent and cutting off agitation entirely to clear a flooded extraction column. Also, typically extraction columns operate at their highest efficiency as you approach the flood point. So just by pushing the column to the flood point and backing off when we're running a pilot test, we'll be able to operate the extraction column under its most efficient conditions, at least from a capacity and agitation standpoint. This slide essentially just shows that how to scale up from a pilot scale column to a commercial scale column, and really it comes down to the technology that was tested. So there's different relationships and equations based upon the type of extraction column technology that was tested during a pilot test. Later in today's extraction presentation, I'm going to be going through a pilot test example of a car column where I'll show this in a little bit more detail. So a quick overview on our pilot plant in Houston. We have a pilot plant where we test essentially nearly all of the extraction processes that we scale to commercial scale. We test there by us testing them at our site, or by allowing a client to rent a column from us or purchase a pilot scale column from us. With a successful pilot test, we can provide a process performance guarantee on a commercial scale extraction column. Within our pilot test in Houston, we can test car columns with plate stacks as high as 20 feet, Scheible columns with as many as 150 agitated stages. Sometimes we'll also test distillation for solvent recovery or downstream purification steps following an extraction test, so we have that capability as well. And the typical analytical capabilities that you'd expect for our pilot facility, we also have in Houston, like GC, HPLC, and IC. And basically, if we can't do the analysis that's required in-house, we can work with other local labs, labs local to the Houston area, like SGS, for any other type of analysis that's required for a pilot test. So Don, myself, and Tom Lightfoot, who's our pilot plant manager in Houston, we put together an article for CEP magazine a few years ago that gives a really good overview on how we design a pilot test, really so we can rapidly optimize an extraction process with the minimum amount of feed and solvent, and generate data from that so we can scale up to a commercial column with a process performance guarantee. If there's any interest in anyone in this article, you can reach out to Don, myself, or Mauricio, and we'd be happy to send you a copy of it. This is what a typical pilot plant setup looks like for an extraction process that we'll test in Houston. We have mass meters on the feed and solvent lines, so we know the rates going in. We often use heat exchangers and either jacketed glass or heat tape around the extraction column itself so we can control the process temperature. We have pumps on the feed and solvent lines going into the column. And then we almost always have a heavy phase pump, which for this example is the raffinate, to control the interface. And I would say 95% of the processes that we test in Houston, we use glass shell extraction columns. And the real benefit there is that you can see everything that's taking place within the column. Things like flood points, you can really identify when flooding's taking place very quickly. Also the impact of coalescing on the internals, that's something else we can look at. And also emulsion bands, entrainment, and rag layers, as I discussed earlier. So there's a huge benefit to testing in glasses, which is what we do, I would say 95% of the time. So now I'm going to go through the pilot test case study that I discussed earlier. And this was a test where we were looking to recover carboxylic acids from fermentation broth. We've done a lot of work with fermentation broths, I'd say, over the past 10 to 15 years. There's been a lot of interest in renewable chemicals and biochemicals from fermentation broths over that time span. So we have a lot of experience in this area. For this particular process, we had a feed stream that contained 5% acids. And the goal was to recover 95% of those carboxylic acids from the feed stream. And the client that we were working with actually had done some of their own equilibrium test work. They identified ethyl acetate as an ideal solvent, but they found that it emulsified really easily. And they actually tried running a pilot test themselves using a type of extraction technology called a rotating disc column. But due to the variable shear, like a Scheible column with an RDC column, they found that the operation was difficult because it had such a strong tendency to emulsify. And then when they were able to operate, they weren't able to get the target amount of acid recovery that they were looking for, only less than 90%. Furthermore, they also had to use a high solvent to feed ratio of 2, which would lead to higher than anticipated operating conditions in a solvent recovery column in a commercial process. So they wanted to lower that as well. So essentially, since this system had such a strong tendency to emulsify, we knew a car column was going to be required. And this is what our pilot setup looked like for this particular test program. It was a 1-inch diameter car column. The majority of the time when we test in a car column, it is 1 inch in diameter, and we can very confidently scale up from that. We do that all the time. The plate stack was 12 feet high. Besides that, it's essentially the same as the slide I showed earlier. However, the one difference here is that the solvents disperse and the feed's continuous. So here is an example where we're taking advantage of the Marangoni effect, with the mass transfer going from the continuous feed to the dispersed solvent. So now I'm going to go through a series of runs that show how we optimized this extraction process. The first 3 runs, we were running with a fixed plate stack height, fixed capacity, a fixed solvent to feed ratio, and we just started pushing the agitation speed. And at 50 strokes a minute, we flooded. We then tried reducing the plate stack height and essentially keeping everything else the same. We're still running at ambient temperature. And here at 40 strokes a minute, we flooded. So this really showed how sensitive the system was to shear and its tendency just to emulsify very easily. We then tried increasing the plate stack height to 10 feet. Here we made spec, but we were looking at the solvent to feed ratio, and we thought we could reduce that a little bit. So we went back to 12 feet of plate stack height. That's what we did in runs 7 through 9. Here in runs 7 and 8, we made spec, achieving greater than 95% extraction of the carboxylic acids. Then we tried increasing the temperature, and this was the key parameter change when we were running this pilot test. By doing that, we were able to recover greater than 98% of the carboxylic acids. So here we really blew the spec away. Then our next step was to take data from the pilot test and design the commercial scale columns. So we looked at runs 7 and 11, which are formatted in bold here, and we used that for scaling up. And the reason we did that is because we wanted our customer to have the flexibility of running at ambient conditions in addition to elevated temperature conditions. So this slide shows how we scaled up to the commercial design. One nice thing about a car column is it's a 1-to-1 scale up based upon capacity. So since we knew that in run 7-11 we were running at 650 gallons per hour per foot squared, we maintained that capacity for the commercial scale up diameter, which resulted in a diameter of 22 inches, since we knew the feed rate for the commercial design and the optimal solvent to feed ratio, which we determined through pilot testing. There are a couple equations on here that show how we scaled up to the commercial plate stack height, which is 38 feet, and the commercial operating speed, which is 32 strokes a minute. And those are just relative to the commercial and pilot diameters. This is what the commercial column looked like. Like I said, in the agitated section, it had a 22-inch diameter. The plate stack height in the agitated section was 38 feet. We put expanded ends on both ends of the column just to mitigate any entrainment due to the reciprocating agitation within the car column. And the overall height was about 50 feet. This was part of a complete modular system where we supplied both the extraction column and the downstream distillation columns as well. And this is what that modular system looks like. You can see the photo on the right. That's the complete system installed at the site. And on the right-hand side of this slide is kind of a CAD drawing, a CAD output of the modular system. On the left-hand side of that CAD output is the car column. On the right-hand side, the large column there is the solvent recovery column. This is really analogous to the slide Don discussed earlier, where we kind of went through the whole system for a typical acetic acid recovery system. The smaller column on the right-hand side of that right module is the raffinate stripping column. And you can see that this system was supplied with all the other necessary equipment like heat exchangers, pumps, has all the piping, all the instrumentation was provided as well, and a complete control system was provided as well as part of this complete modular system. If anyone has time and they're more interested on pilot testing and some of the other things I discussed, there's a video that you can find, like most other videos on YouTube, where it's a 10-minute video of just the pilot car column, and it goes through a lot of the things I discussed earlier that we see when we pilot test, like the impacts of wetting characteristics, coalescing, emulsion bands, and flooding. So if you have some time and you're interested, I think this is really worth a watch. And there will be a link to this included in the presentation.
Great, thank you, Don and Brendan. Appreciate you rushing through there was a lot of material to cover in the hour, so appreciate it. Here are the contact details if anybody wants to reach out to Don and Brendan afterwards. As I mentioned, we will be summarizing all the questions and answers after this webinar and submitting it to all the attendees. There's also a link to the recording of this video and the article that Don and Brendan had authored a few years ago. Also wanted to point out that next month we're going to be doing another webinar about redesigning solvent recovery systems for optimal efficiency and reduced OpEx. It will be March 23rd, presented by Tom Schaefer, our Vice President and subject matter expert on this. Here's a link to it. It's not clickable, but I'll also provide that when we revert back to you all later after this webinar. So definitely, thank you everybody for attending our webinar. And sorry we ran over just 2 minutes, but look forward to seeing you all in the next webinar. Thank you. Take care.